Here's something that sounds impossible. Google just released an AI model that can look at a photo, read a document, and understand a chart, but it threw away the one piece every other vision model swore you absolutely needed. It's called Gemma 412B, and it landed just yesterday. For years, every model that could see worked the same way. You bolted a separate camera brain onto the language model, a chunk of software called a vision encoder, whose only job was to translate pixels into something the text model could digest. Think of it like hiring a translator who stands between your eyes and your brain, converting everything you look at into words before you're allowed to think about it. Gemma 4 fires that translator. It processes images and text in the exact same stream, with the exact same machinery, no middleman. Google calls it encoder-free multimodal. And the 12 billion in the name refers to its parameters, the adjustable knobs that store what the model knows. To put that in perspective, 12 billion is small enough to run on a single consumer graphics card, yet it's matching models several times its size on vision tasks. That's the wait what moment. A model you can run at home, with a radically simpler design, beating the giants at reading the world. So how did Google pull off something the entire industry assumed was a hard requirement? And here's where it gets interesting. To understand why this is a big deal, you have to know how AI learned to see in the first place. Rewind to 2021. A model called CLIP showed that if you trained a vision system on millions of image and caption pairs from the internet, it could link pictures to words shockingly well. So that became the recipe. Every multimodal model since then has been two brains stitched together. One brain, the vision encoder, stares at the image and boils it down into a compact numerical summary. The second brain, the language model, takes that summary and reasons about it in words. It worked, but it came with hidden costs. Imagine reading a book where someone else summarizes every page for you before you're allowed to turn it. You're fast, sure, but you only ever see their summary, never the raw page. Fine details get lost in translation. Worse, you now have two separate systems to train, tune, and keep in sync, which means more memory, more compute, and more places for things to break. Engineers accepted this as the cost of doing business. The vision encoder was treated like a law of physics, just how multimodal AI works. Companies poured enormous resources into building better encoders, some with hundreds of millions of extra parameters bolted on just for the seeing part. Nobody seriously questioned whether the translator was even necessary. And that unquestioned assumption is exactly the thing Gemma 4 just walked up to and quietly demolished. But how do you teach a model to see without it? So here's the clever part. A language model doesn't actually read words. It reads tokens, little numbered chunks of text, and a transformer, the engine inside, is really just a machine that finds patterns between tokens. The insight behind Gemma 4 is almost embarrassingly simple. What if an image is just another kind of token? Instead of running the picture through a separate encoder, Gemma 4 slices the image into a grid of small squares called patches, the way you'd cut a photo into postage stamp tiles. Each patch gets turned into a token, the same flavor of token the model already uses for words. Then it all goes into one pipeline. Words and image patches sit side by side in the same stream, and the same transformer chews on both at once. There's no translator standing in between because there's nothing to translate. The model learns the connection between a picture of a cat and the word cat directly, end to end, instead of through a handoff. The payoff is concrete. By dropping the separate encoder, Gemma 4 cuts out an entire stage of processing, which is part of why a 12 billion parameter model can keep pace with rivals carrying far more weight. Fewer moving parts means less memory, faster responses, and one system to train instead of two. It's the difference between a relay race with a fragile baton handoff and a single sprinter who never has to pass anything. And once you see images and text as the same thing, something surprising becomes possible. Let's get concrete, because architecture talk means nothing if the thing can't perform. Point Gemma 4 at a messy restaurant receipt, crumpled and badly lit, and ask it to total the items and work out the tip. It reads the numbers straight off the image and does the maths, no special document scanner required. Hand it a dense financial chart, the kind with 3 overlapping lines and a tiny legend, and it'll tell you which quarter revenue peaked and by how much. Show it a photo of your fridge, and it'll suggest 3 dinners from what it spots inside. Because text and pixels share the same pipeline, you can even mix them mid-conversation. Snap a picture of a broken bike derailleur and type, "Which part do I replace?" and it reasons about the photo and your words together as one thought. Developers are already testing it on screenshots, turning a picture of an app interface into a description of every button. One early demo had it reading a handwritten whiteboard full of equations and converting them into clean-typed formulas. The reason this small model handles all of that is the unified design. Detail that a separate encoder would have compressed away stays available, so fine print, faint lines, and small symbols survive. 12 billion parameters running on hardware a hobbyist can afford, doing work that 2 years ago needed a data center. But raw capability only means something when you stack it against the competition. So how does it actually measure up? Now for the part that makes engineers do a double take. On standard vision benchmarks, the tests the whole industry uses to rank these models, Gemma 412B trades blows with systems carrying 2, 3, even 4 times as many parameters. Think of it like a lightweight boxer stepping into the ring against heavyweights and walking out with the belt. Against its own predecessor, Gemma 3. Google reports meaningfully sharper results on document reading and chart understanding, the tasks where that lost detail used to hurt most. Compared to other open-weight rivals like the larger Llama and QN Vision models, Gemma 4 lands in the same performance neighborhood while using noticeably less memory to run. And memory is the whole game when you're trying to fit a model onto one graphics card instead of a rack of them. A heavier model might score a point or two higher on paper, but if it needs 40 gigabytes of video memory and Gemma 4 needs a fraction of that, the smaller one wins in the real world, where most people don't own server farms. There's a catch worth naming. Benchmarks aren't the same as your actual job, and a model that aces a chart reading test can still stumble on your weird, specific data. But the trend is unmistakable. The performance per parameter is climbing fast. And the encoder-free design is a big reason why. That efficiency isn't just a nerdy bragging right, though. It quietly reshapes who gets to build with AI at all. Step back and the real story isn't a benchmark, it's a shift in power. Gemma 4 is open weight, which means Google publishes the actual model file for anyone to download, run, and modify free. Contrast that with the closed systems where you rent access through an internet connection and your data leaves your building every single time. With an open model small enough for one graphics card, a hospital can run image analysis on its own servers without patient scans ever touching the cloud. A startup with no budget can fine-tune it on their niche data and ship a product. A researcher in a country with no access to expensive cloud credits can still do serious work. That's the quiet revolution here. For most of the AI boom, the cutting edge lived behind paywalls, controlled by a handful of companies with the biggest data centers. Every step towards small, capable open models hands a little of that control back to everyone else. And the encoder-free design pours fuel on it, because simpler and smaller is exactly what you need to squeeze a model onto a phone, a car dashboard, or a factory camera that has no internet at all. Picture a drone inspecting a wind turbine, spotting a hairline crack on its own, with no signal needed. There's a flip side worth respecting. Powerful vision models running anywhere, with no oversight, also means deepfakes and surveillance tools get cheaper and harder to trace. The same openness that empowers a researcher empowers a bad actor. So how do you actually get your hands on this thing? Here's the genuinely exciting part. You don't need a lab to try this. If you've got a reasonably modern graphics card with enough video memory, you can run Gemma 412B on your own desk this weekend. The easiest path is a free tool called Llama, which handles all the messy setup for you. You install it, type one short command to pull the Gemma 4 model, and within minutes you're chatting with it and feeding it images from your own folder, completely offline. No subscription, no data leaving your machine. If your card is on the smaller side, you reach for something called a quantized version. In plain English, quantization shrinks the model by storing its numbers with less precision, like saving a photo as a slightly lower quality file. It trims the memory needed by more than half, with only a tiny dip in accuracy, which is often the difference between fitting on your hardware or not. For builders who want to go deeper, Google ships Gemma 4 through the Hugging Face library, the standard toolkit where developers download and fine-tune open models in a few lines of code. That's where the real magic lives, because you can train it on your own images, your own documents, your own problem, and make it an expert in your specific world. Start small. Pull the model, show it a photo, ask it a question, and watch a 12 billion parameter brain reason about something you took on your phone 2 minutes ago. Once you've seen it work on your own machine, the bigger picture really lands. So what does all this actually mean for you watching this tonight? Here's the takeaway. Gemma 412B is a signal of where AI is heading, and the direction is smaller, smarter, and far more open. The vision encoder, a component the entire industry treated as untouchable, turned out to be optional, and dropping it gave us a model that runs on hardware you can buy at any electronics store while keeping pace with the giants. That pattern, doing more with less, is the trend to watch over the next year. The frontier is quietly moving from who has the biggest data center to who has the cleverest design. Here's what to keep an eye on next. Watch for these encoder-free, unified models to start showing up inside phones, apps, and devices that work with no internet at all, because that's exactly what their efficiency unlocks. And watch the open weight movement, because every release like this hands a little more capability to ordinary developers, students, and small businesses instead of a handful of tech giants. If you build anything, this is your invitation to download Gemma 4, point it at a real problem, and see what a free model can do. The barrier to entry just dropped through the floor. If this made the future feel a little closer and a lot more understandable, follow for daily AI news, because this space moves fast. And I'll make sure you never get left behind. I'll see you in the next one.